Mark P. Otten back with you.
All right, so this is your introduction to regression video, and this is a continuation of your correlation video using the same data. And there's an important theoretical difference between correlation and regression, but in terms of the math, they kind of go together. So I'm going to clarify what that means here as we go along. The theoretical difference is that we are turning one of our variables into an independent variable and the other into a dependent variable. So if you go back to your roadmap of hypothesis testing, this is important because when we're doing a correlation, we're not assuming any sort of causation, which is the foundation of it, and why we'd run a correlation in the first place. And so in this case, we were assuming before that there may be a relationship between mother stress and the health of the baby or the birth weight of the baby, but one is not causing the other as much as the other is causing the one. So there was no causation there. Now, if we turn this into a prediction with the mother's stress, let's say at a certain point early in the pregnancy, then theoretically causing changes for the baby's health or the eventual birth weight of the baby, then we have a prediction that implies that the cause is the stress and the effect or the dependent variable is the health of the baby or the birth weight. So if we turn it around like that, we're not saying now that birth weight could cause mom's stress. And the way we could do that here is just by saying, well, mom's stress occurred, let's say, in the past during pregnancy, and then the baby's health occurred when the baby was born or was assessed when the baby was born. So that way, we can't imagine the health of the baby when it's born, then in turn causing mom to feel anxiety in the past, right? So then it's no longer a correlation, it's a prediction. We have an independent variable, we have a dependent variable, and it's no longer appropriate to use a correlation. Now we move toward a regression approach, which again, mathematically is going to be related. The distinction in terms of the math becomes more different. Regression becomes more different than correlation once we get to the more advanced regressions that we'll get to a little bit later in this class with two independent variables. For now, the math is going to look pretty similar. So, in fact, we've already done a lot of the work when we calculated our correlation. So here's the data. We're going to reuse this data for this example for families. This is the scatter plot. Now, what I've done on the slide here is I've drawn in the regression line. And we can get this on SPSS if we want, but this is not really a big deal. What I'm showing you is the line for illustrative purposes here. The line is going from top left to bottom right, so we already talked about how that implies a negative correlation. We already actually calculated the negative correlation. It was negative 0.708, I believe. And the way that line is drawn is not just by eyeballing it here, it's actually by some math that we'll get to here in this video. The other thing that I drew in there was the bubble that I was describing in the correlation video. The bubble tells us that if it's thin right around that line, if the bubble that is thin, then that means that the correlation is stronger. If it's more like a circle, if it's really, the bubble is drawn really far away from the line or just sort of randomly compared to the line, then the correlation is very low. So this regression line is drawn in, but how is it done? Well, the theory here is we want the line of best fit through the points. So technically what this is a line that minimizes, okay, so this is a mouthful. Let's walk through this here. Minimizes the sum of squared vertical distances from all points to the line. So what does that mean? Well, let's go back to the graph. Suppose you draw vertical lines from the points to the line here. You take that point in the top left, and you draw, it's going to be pretty short, a vertical line. Not a line directly to the regression line, but one that's vertical that goes down to the line. Same thing for those other ones. Looks like maybe the point in the bottom right there, the point with the anxiety value of about 6. I think that's 6.1 on the anxiety scale. That one you'd have to draw and also extend the regression line down so that a vertical line will hit it eventually. That one looks a little bit longer, right? So the dots that are farther away from the line have greater distances from vertical distances from those points to the line. So when we talk about minimizing the sum of squared vertical distances, we're taking vertical lines, drawing them from each point to the line, and then squaring those distances and adding them up. So you take, again, that top left value, it's a pretty short vertical distance from the point to the line. That, let's say, it's above the line, so that's a positive value, whereas the two dots that are below the line, those would be negative values. If we square them, however, we're making all of those distances positive, and then that allows us to add them up as a collection of summed squared vertical distances. So this is why regression is known as least squares, because you're trying to minimize these squared vertical distances. Let me go back one more time. So suppose we drew a line that was just way off, that was like a horizontal line at the far top of this graph or something like that. And all the points were really far from that line. You'd see those squared vertical distances, or those drawn lines from the dots to the line, those would be really long. So what ends up happening is that this line, this regression line that goes right through the middle of the point, mathematically ends up being the one that has the smallest distances from each dot to the line. Theoretically, then, you could draw this regression line by guess and check. You could draw one, check the vertical distances, add them up. Then draw another one, check the vertical distances, add them up. And you'd have a whole bunch of lines, and then you end up with the one that was the lowest. But that sounds like a lot of work and really unnecessary in this case. That's the theory, though, of how this line then gets plugged into the middle of these dots. So how do we actually get it? Well, we use the equation for a straight line, which you may have seen in your, I don't know, geometry class in high school or something like that. When I first saw this equation, it was, the letters were a little different. It was like y equals mx plus b. Now, statisticians have changed the letters but kept the equation the same. So now the m becomes a b and a b becomes an a. I don't know, maybe you just get those old letters out of your head when you're studying this particular part of the lesson. Now we have y equals bx plus a. B is the slope of the line, and a is going to be the y-intercept of the line. So for our example, y was baby's birth weight. That's y is declared as the dependent variable. X is declared as the independent variable. In this case, mother's anxiety is x, and then you get your slope and your intercept like so. So the larger the slope is, or the larger the b value is, the more vertical the line is. And so you saw our line for our particular scatter plot here was pretty steep, suggesting that the slope is quite large potentially, and also negative. The a is the y-intercept, so that's where the value of y the value of y where the line crosses the y-axis. So let's go back to the graph here. The slope then is negative here, and it's pretty steep. We don't have the number for it yet, but we can say that it's steeper. It looks more vertical than horizontal, I'll put it that way. And then if you were to extend this line out to the point where it crosses the y-axis over there on the left, then you'd have the y-intercept value. So those two values then, the slope and the y-intercept, define the line. And once you know those two values, you can then draw a line or draw dots on the line and illustrate the whole thing as we've done. So how do we get these values? Well, we're going to get them from SPSS, but we're also going to get them from some calculations here. Again, you've done most of the work actually. The b value is derived from the correlation that we just calculated in the last video, and then the a value is derived from the b value. So it's important, I think, in this case to do the correlation first, the b value or slope second, and the a value third. If you do that, you're not doing any extra work as you go along here. Okay, so what this ultimately is going to do is it's going to allow us to make predictions about future families, and that's the cool part of regression that we're going to see a little bit here. And then again, when you get into the case where you have two independent variables, it becomes even cooler in that case. All right, so we're going to switch over to SPSS and Excel for the next part. Okay, so we're back to our anxiety birth weight example in SPSS. This is again a a repeat of our correlation video. So this time we're going to run a regression. We're going to get the regression line, and we're going to get the slope and intercept values that go along with it. So the first way to do this, I'm going to go back and get a scatter plot again, and this way we can see the regression line actually in action or on the graph. So I'm going to go to where I went before, which is graphs, legacy, dialogues, and then scatter / dot. Okay, it's a very strange collection of labels. All right, anyway, you can keep simple scatter as the default choice there, and I've already moved these over so you can see what I've done. You can move mom's anxiety over to X, birth weight over to Y. Again, it doesn't really matter which you put where, but you should probably try to keep it consistent from, let's say you got the scatter plot when you did the correlation before. I'm just trying to keep it consistent from there so it looks the same. So I'm going to go ahead and click OK, and we'll get our scatter plot again. This is again a repeat of the correlation video scatter plot. And then from here you're going to double click, so you can double click anywhere inside this graph area to get some more options. And in fact, there's tons of options that I haven't even scratched the surface of here for you guys, just as far as changing colors, doing different things in SPSS. But for the purposes here, once you double click on the graph there, I'm going to go up to this little icon here. It's like, and I'm assuming this will look similar on your screen. There's this top 3 rows of icons here. It's the 3rd row and about the 5th icon over from the left. And when I hold the cursor over it, it says add fit line. What did it say again? Add fit line at total. That's your regression line. So you click on that, and it automatically pops up a window here that you can just close, and it automatically puts it in there. And then you can exit that out, and it will put it in the regular SPSS output window for you. So there's the line. It's automatically drawn according to the equation for a straight line, which, as it's labeled here, is y equals 8.36. That's your y-intercept value, or your a value, minus 0.37 times x. So negative 0.37 is going to be your slope, or your b value. And then the r squared value, which we'll get to in a second, is up here at 0.501. So actually, some of the statistics have already been done for you, but I'm going to go back and do one more thing, which is the more conventional way to get those statistics, and that is to click on Analyze, Regression, and Linear, and for us to plug in our 2 values in this window here. So here you're going to put your x value into independent variable, because that's what it is. Independence is the area where the independent variables go. Dependent is where the dependent variable goes. And that's birth weight in this case, which I just misclicked. There we go. It goes over to dependent variable. And we're going to go ahead and click through and click OK. All the default options should be fine. And here is your more conventional regression output that you might get if you run let's say a regression with an additional independent variable, which is what we're going to do here shortly in the next few weeks. Okay, so first we're going to look at the last. That gives you 4 boxes. So we're going to look at the last box first, and you're going to see the statistics that you need. So they're labeled kind of strangely. The A value is actually 8.362 here under the unstandardized capital B column, which is odd labeling. The B value here, lowercase b, negative 0.371. That's in the same column, and then in the mom anxiety row. So your A and B values are there located in that first column. You might notice the 0.708 here. That's your correlation value actually repeated as a beta, which we'll talk about betas again when we get to the 2IV regression later on. And the other statistic that we will note for the moment here is the 0.292. That also should look familiar. That was the p-value that went along with your correlation. And here it's also the p-value that goes along with your regression. So we'll interpret that in a second. The other statistic that we'll interpret in a second is that r squared value here, 0.501. And so we'll talk about that momentarily as well. But we've now had SPSS get us our slope and intercept values, and we have not calculated them ourselves, so we need to go back and do that. So let me pull up my Excel window here. So this one is your, if you've watched the correlation video and performed a correlation here in the past, this is should look familiar. This is what we entered in before. So we did all this work. We got this Pearson's R value for our example of 0.7078 negative. So I've said in this video, you've done most of the work. So what have you done? Well, I'm going to get our B value next. This is our slope, and then we're going to end up with an A value here for our intercept. The B value is just, I'm just going to type it right in. We're going to click on equals. We're going to click on the correlation. You're going to take the correlation, you're going to multiply it by the standard deviation of y and divide by the standard deviation of x. That's all you need to do to get the slope value. So you can tell mathematically the correlation is going to be very much related to the slope value. And it's related by a factor of standard deviations. So you're kind of putting the correlation, what you're doing here is you're putting the correlation back into units of, instead of z-scores, back into units of y and x. Technically is what's happening there. You're changing the unit that it's measured in. And switching it back to a slope, which is given there, 0.37 negative. So again, once you've done the correlation's a lot of work, but the slope value, once you get the correlation, is not so bad. Okay, so for the A value, again, you've done most of the work already. You're just going to take the mean of y, which is 6.935 in this case, and subtract the slope times the mean for x. And this is sort of an algebraic way. You've already done most of the work getting the slope, so it's an algebraic way of turning the slope kind of backwards through the regression equation into an intercept. The algebra works out nicely for you to have already completed most of the work still in getting the correlation. So the A value then comes out to be 8.36, and these values should match what you got in SPSS. The only remaining value to talk about is the R squared value, and so if we just square R equals R caret 2, you're going to get your R squared value. That caret, by the way, is capital 6 on your keyboard. That's going to give you your R squared value of 0.501. I'm going to allow you to just pull that from SPSS as well. So there's how your values came about for your regression. Okay, so what this allows us to do then is make predictions about future families or make predictions about future baby birth weights based on our equation here. So I'm going to just type this in as a text here. So your equation is y equals the slope, which is negative 0.37 x times x, plus the intercept, 8.36. Okay, so that's your regression equation. Now suppose a new family comes along. Now this is one of the cool parts of regression. Suppose there's a mom who comes in and has a score of anxiety of, let's say, 5 on the scale of 1 to 10. We can now predict, based on this information, the birth weight of her baby. So we would do that by going equals negative 0.37, that's the slope, times 5, right, plus 8.36. And if you plug in 5 for x like so, you're going to get a predicted value 6.51 for the baby's birth weight. You can see these changes as you go along. So for example, if you replace the 5, let's say the mom is like super stressed out, like on a 10, right? You go equals negative 0.37 times 10 now, plus 8.36. And that baby's birth weight now has dropped to 4.66 in the predicted value. And the value of the regression equation is, if it's a good regression equation, if that anxiety is a good predictor of the dependent variable. That is, if the mother's anxiety is doing a lot to help us know or be able to predict what the birth weight is going to be, then that's going to be very helpful, and that's going to be a nice research finding to talk about. Because let's say you want to help pregnant mothers in this case, and you want to encourage them to do the right things in their lives to achieve health for their baby, then you can show them, so this turns into a research finding, and you can then advise as a doctor or as a psychologist how to help a family. So anyway, this is just 4 families, so we can't tell too much, but that leads us to our final couple of conclusions here, going back to the lecture notes. Okay, so our last couple of conclusions to be made. SPSS also gives us that p-value that I mentioned earlier. So the 0.292 here for our example is in the lower right corner. It's in the row that is labeled mom's anxiety for this example. And in the last column, they're labeled sig, or a p-value. So what that means, 0.292 greater than 0.05, is in this case we are not rejecting our null hypothesis, right? And we're saying that our slope is not significantly different than 0. And so in this case, the null hypothesis was that the slope is 0. The alternative hypothesis is that the slope is not 0. Okay, so what that means is that our slope is not so a slope of 0 suggests that there is no angle to our line, right? And there is no relationship in this case between our independent and dependent variables. Let's suppose the slope were 0, it would be like a horizontal line. And so like on a horizontal line, the independent variable x, right, as you're going from a lower value to a higher value, it stays the same. And so then there is no relationship between x and y. There is no relationship between the independent and dependent variables. So in this case, we're saying that our baby's birth weight and our mother's anxiety are not significantly related to each other. Yes, the slope was different than 0 in value, but it was not different enough to conclude that it is significantly different than 0. In the end, we're not really concluding anything new about this data because we already said the exact same thing for the correlation between mother's anxiety and birth weight. So the numbers don't change. In this case, the p-value is the same whether you do a correlation test or whether you do a regression test. So the regression test in this case is kind of like, we didn't really do anything new. We already knew that baby's birth weight and mother's anxiety were not significantly related. So now we're saying that mother's anxiety is not significantly predicting or significantly leading to changes in or causing changes in birth weight. However you want to say it, it's the same result. And it's, again, because of small sample size, very likely that there was no relationship here seen. So we're not saying anything new. The regression's like, it's kind of redundant, but when we get to the 2 independent variable regression, I've been previewing this a lot in this video. You must be really on the edge of your seat once we get to add in that second independent variable. Once we get there, you'll see the difference between a test of a slope versus a test of a correlation, and then you'll maybe understand a little bit more why we need both. But meanwhile, here we're again concluding with the null hypothesis and saying that the slope is not significantly different than 0, or that mother's anxiety does not lead to significant changes in baby's birth weight. The last one here is the r-squared value. So if you look over again in the SPSS output, it's 0.501, or you can just take your correlation and square it as we did in Excel. This is the effect size value for regression. So we already evaluated our hypothesis test. And so now effect size, as I mentioned before in the Cohen's d video, effect size is very important. It's not part of the hypothesis test, but it's sometimes even more important in order to evaluate your study relative to other studies. Will this effect, if it's there, will this relationship or lack thereof between mother's anxiety and birth weight, will that carry over to the next study? Is it something that could be replicated, or is it something that could not? So a large r-squared here suggests a strong relationship between baby's birth weight and mother's anxiety. We have a 0.501, so to interpret, we convert that to percentage. So 50.1% of the variance in the baby's birth weight is explained by mother's anxiety. So if you know the mother's anxiety level, you have 50% of the information needed to understand or predict what the baby's birth weight is going to be. So with only 4 families, that's pretty good, actually. It's pretty high. There's no specific cutoff point for what's high and what's low here. In your homework, you can just report the value. But then when we compare it to multiple studies, we can see, let's say, several more samples of data, pregnant mothers and babies, and maybe they don't have the same R-squared value, 50%, that we did here. Then we can start to conclude something about the size of this effect. Okay, that's it for regression, at least for now.